Albert Einstein is known around the world as perhaps the greatest scientist of the 20th century. His accomplishments even brought him to transcend science and become a pop cultural icon. However, very few are actually aware of his revolutionary contributions to science, the theory of relativity. Relativity is divided into two separate theories, special relativity and general relativity, the completion of which are roughly a decade apart. Both of these game-changing theories arose out of a need proposed by turn-of-the-century physics. For 300 years, Newton's laws of motion were known to govern the universe. However, they could not account for the discrepancies in certain things, such as planetary motion. They also failed to line up with Maxwell's equations. Therefore, Einstein conceived of a new theory to explain motion, specifically with respect to time. This new theory, the special theory of relativity, redefined how time worked. Einstein began with two postulates, that the laws of physics are invariant, that is, the same, and that the speed of light is the same in all inertial reference frames. An inertial reference frame is any frame of reference that is at a constant velocity and not undergoing acceleration. To accomplish these postulates, Einstein incorporated Lorentz transformations. Lorentz transformations are a mathematical idea that treats time, instead of as a separate entity, as part of a four-dimensional space called Minkowski spacetime. It also treats all inertial reference frames as equivalent, as is required by Einstein's postulates, and allows one to translate between two different reference frames, A and A prime. The speed of light is treated as a constant, c, which allows it to remain the same, regardless of the reference frame it is observed from. At low velocities, the special theory is indistinguishable from Newton's laws. This is because as velocity approaches zero, the Lorentz constant tends to 1. However, as the velocities approach the speed of light, the Lorentz constant approaches infinity, resulting in some weird results at high velocities. First off, it implies that the concept of simultaneity no longer exists, as time can be scaled just as much as space in different reference frames. Time can also be slowed at high velocities from the perspective of outside observers. Finally, at high velocities, matter can also be squeezed from the perspective of another inertial reference frame. To the amazement of everyone, this theory, formulated with almost no experimental evidence, happened to perfectly account for the things that Newton's failed to. However, special relativity is just a special case, hence the name special relativity. It is only relevant in weak gravitational fields. The complete version of Einstein's theory, the general theory of relativity, was completed about 10 years later. This paper, instead of dealing with time, accounts for the phenomenon we know as gravity. This theory involves non-inertial reference frames, the frames of reference that experience acceleration. The math that Einstein used for this ended up being quite a bit more complicated than the special theory, with the incorporation of the calculus of metric tensors and pseudo-Riemannian manifolds, both of which are too complicated to touch upon in this video. Instead, an intuitive approach will do. Imagine you are a pencil in a pencil box. When you are at rest, you are in an inertial reference frame. However, when someone picks you up and drops you, you accelerate towards the center of the earth in what we know as gravity. You are now no longer in an inertial reference frame. However, if someone instead picked up the entire box and dropped that, it would feel like there was no gravity from your perspective, at least for a few seconds. This situation represents something in free fall, and it turns out that this situation is indistinguishable from being outside the reach of a gravitational field. It turns out that the space-time mentioned earlier can be bent by masses sufficiently large enough, such as the Earth or the Sun. The gravitational fields in space are actually just space-time that is bent. The motion of an object through space-time will always be the shortest path, although it may not be the shortest path through space. Although the distance in space or the interval of time may be bent, the space-time interval will always remain constant. This theory also predicted the existence of areas of space-time that have infinite density, which we now know as black holes. Einstein's theory has been shown to be correct according to all modern experiments. However, it seems to contradict quantum theory, the other pillar of 20th century physics, which is also very well documented experimentally. This means that although Einstein's theory of relativity was successful, a more complete version of physics awaits.